Hello, everyone. We're going to start in about a minute or so. And happy spring to everyone. It just started the other day. So hopefully you're enjoying the spring. Okay, it is 6 p.m. and we are going to get started. Good evening, everyone, and welcome to EBMUD's Water Wednesday series. My name is EBMUD Burrell, and I am a Community Affairs Representative at EBMUD, and I will be your host for tonight. Water Wednesday is a monthly event where we talk about important topics pertaining to our water and wastewater. For tonight's discussion, our speakers are UC Berkeley Professor Kenichi Soga and EBMUD General Manager Clifford Chan, who will be talking about UC Berkeley's Center for Smart Infrastructure. And that's a partnership that applies cutting-edge technology to tackle infrastructure challenges caused by climate change, aging systems, and natural hazards. All of our Water Wednesday events are recorded and posted within a week from viewing at ebmud.com/Water Wednesday. And by attending tonight's event, you do consent to be virtually recorded. If you have any questions during the presentation, please feel free to post them in the Q&A function throughout the presentation. Tonight, we have EBMUD Senior Community Affairs Representative Catherine Horn, who will answer questions as we go along. We will still reserve some time at the end for questions. If you think of a question after the event is over, feel free to send us an email at waterwednesday@ebmud.com. That email address will also be shared again at the end of this presentation. So, before we begin to show the slides, I would like to give you some background information about our speakers. Clifford Chan was appointed to serve as the 11th General Manager of EBMUD Utility District in June 2020. In his role, he oversees delivery of high-quality drinking water to 1.4 million residents and businesses in 20 cities and 15 unincorporated communities in Alameda and Contra Costa counties. He manages an organization with 2,000 employees and supports a 7-member publicly elected board of directors. Mr. Chan's education includes a Bachelor in Civil Engineering and a Master of Science in Geotechnical Engineering from the University of California, Berkeley. He is a member of the American Water Works Association and the Association of California Water Agencies. He currently serves on the board of the California Urban Water Agencies. Our second speaker, Professor Kenichi Soga, is the Donald H. McLaughlin Professor at UC Berkeley. Soga is also the director of the Berkeley Center for Smart Infrastructure, a faculty scientist at Lawrence Berkeley National Laboratory, and serves as a special advisor to the Dean of College of Engineering for Resilient and Sustainable Systems. Soga's research focuses on infrastructure sensing, performance-based design, and maintenance of infrastructure energy geotechnics and geomechanics. He is also a member of several professional organizations, including the National Academy of Engineering, a fellow for the UK Royal Academy of Engineering, the Institution of Civil Engineers, the American Society of Civil Engineers, and the Engineering Academy of Japan. He is the recipient of several notable awards, including the George Stephenson Medal and Telford Gold Medal for ICE in 2006, the Walter L. Huber Civil Engineering Research Prize for ASCE in 2007, and the UCB Baker Prize for his work on commercialization of smart infrastructure technologies in 2022. And so now we're going to pause for a second. I am going to share my screen as we bring up the PowerPoint. We're going to here. Okay, and we're going to start. And Clifford, it's on you to take it away.
Okay, thank you, EBMUD. I just want to say I'm really honored to be here tonight with Kenichi, really to share some of the exciting work that we're doing here at EBMUD and at UC Berkeley. And as you heard EBMUD talk about, we're going to talk about this partnership on the Center for Smart Infrastructure, or the CSI, between EBMUD and UC Berkeley. This was something that we started a few years ago, back in November 2021. And it's really grown beyond just EBMUD and UC Berkeley, but you'll hear from Kenichi a lot of the other partners that have since joined on. If you go to the next slide. So, at a high level, the question is, like, what is the CSI? And if you think about the industry, if you think about just water utilities, for instance, we have some really big challenges. We have a limited resource, water, that's becoming more limited because of climate change, that's being operated through aging infrastructure, and for EBMUD, some as old as 150 years old, that's interconnected and dependent on other aging infrastructure. And being in California, every day we're at risk of a major earthquake that can really tear apart our entire infrastructure. And we're a public, not-for-profit agency, so we also have limited financial resources because we really have to think about ways to keep our water affordable. And if that wasn't challenging enough, our customers expect that when they turn on their faucet or they turn on their shower, that the water comes out all the time, uninterrupted. So, this isn't some sort of false dilemma that we're facing. We really can address many of these challenges if we collaborate and if we innovate. So instead of thinking about all the challenges I've talked about, I think we can look at opportunities. And I think the biggest opportunity that we have as utilities is we, across the country, are investing billions of dollars in our infrastructure. EBMUD is no different. And so there's an opportunity for us to do things better. Now, historically, we've tried to solve these problems on our own. But the problems that we're facing today are really too big for any of us to do. So the CSI is a partnership between infrastructure owners like EBMUD, academia, industry, consultants, and regulators to help us address those really pressing issues that you see on the screen, like the aging infrastructure, climate change, water supply shortages, or emergency preparedness. And if we do this right, we can build more resilient systems. And what the CSI offers is that they can help us using state-of-the-art testing equipment, sensors and robotics, data and machine learning, and high-performance computing and modeling. And that's really what we hope to get out of the CSI. I just want to see if Kenichi, if you want to add anything.
No, this is great.
Okay, maybe we go to the next slide.
Let's go to the next slide. Yeah, thanks, Clifford. So as Clifford says, that we work with a lot of infrastructure owners and agencies, and because of the EBMUD first support, and then we're growing rapidly to work together with a variety of infrastructure owners, which will be shown in the next slide, if we can. And we work with LADWP, Los Angeles Department of Water and Power, and Metropolitan Water District, San Francisco Public Utility Commission, PG&E. We just joined, Yuba Water just joined, U.S. Army Corps of Engineers. There's a lot of aging facilities that they own, as well as Caltrans. So, and then we also work with California Energy Commission. So these are the infrastructures that we work together because all of these infrastructure owners faces aging infrastructure. How do we bring innovation to our systems? Yeah, thanks a lot for this one. So you can see a lot of things. We also work on wildfire evacuation and wildfire preparedness. So you see Marine Wildfire Prevention Authority is also working together with us. Can we go to the next slide? And I come from UC Berkeley, and at Berkeley Engineering, we have this really exciting initiative led by our Dean of College of Engineering, Professor Sujay Liu, on resilient infrastructure for sustainability and equity. We call it RISE initiative. And this particular RISE initiative is really to bring all the centers, slide 4, all our centers within our College of Engineering working together, but beyond the College of Engineering. So you can see variety of centers that we have for looking at earthquake, how the information technologies are used in the interest of a society, and it's called CITRIS. Berkeley Water Center is looking at water quality and all the water resources. Institute of Transportation Studies are in, because we all deal with transportation, that is what ITS does. Sim Center is a National Science Foundation center to look at simulations from the road level to the Bay Area or big regional level. At the same time, we work with Global Metropolitan Studies, who are the group of social scientists looking about infrastructure. So we're very excited to work with a variety of academics with the infrastructure owners, like what Clifford has mentioned. The spirit here is that we tend to sort of design our infrastructure for 100 years. Sometimes we have an aging infrastructure that is more than 100 years. We want to prolong the life of infrastructure. At the same time, if you look at how the infrastructure used, it changes every 10 years, 20 years, 30 years. And so we say aging infrastructure, not because the material is aging, but also the usage is changing, and that is caused the aging infrastructure. So how can we change this to bring the innovation into the market? And not to be pessimistic about this, we want to be proactive, forward-looking. So it'll be great to say to our future generation, there'll be no more aging infrastructure because we do it right now. So let's move to the next slide.
Yes. So yeah. So I mean, if you look at our service area, I think EBMUD mentioned at the very beginning, that includes 35 cities and communities, and it covers 332 square miles. And under just about every street in our service area is a pipe that brings water to our 1.4 million customers. Now, in total, we have about 4,200 miles of pipe. Now, to put that in perspective, if you put that pipe end to end, you can go from Oakland to Chicago and back again. Now, if you look at the United States, in the United States, there's 1.2 million miles of water pipe. And I was just looking this up today, but if you want to put that in perspective, you can go from the Earth to the moon and back again 2.5 times. And that's how much infrastructure we have to deal with. Now, in California, we live in earthquake country. And you can see the faults on that image on the left that cross our service area. And we want to make sure that our pipes are resilient to those hazards like earthquakes and landslides. So about a decade ago, we started our pipeline rebuild program to innovate how we select pipes that we replace, how we can improve our designs to build earthquake-resistant pipes, and how we can improve the construction process. We really looked at every aspect of how we install pipes because it's expensive. It costs about $2.5 million per mile to replace pipe. Now, an important part of the design process is to test the pipes to make sure that it can withstand the forces of things like an earthquake or other hazards. Now, we used to send our engineers to Cornell University. At the time, they had a testing lab to witness the test of these pipes. About 4 years ago, we heard that Cornell was closing their lab. So I actually approached Kenichi and said, let's move that testing facility to Berkeley. It makes more sense. I mean, this is where all the earthquakes happen anyway. And I think it's really great because right in our backyard is the top civil engineering university in the country. And Kenichi agreed. And the first phase of the CSI was to set up the pipe testing lab. You can go next slide.
So what you see on the right top is the soil box. We call it split basin test box, where you see where the pipeline is buried in the soil, but then the soil, two parts of the soil move relative to each other to create a fault movement. So by doing that, we will test the pipe in the actual soil and see the performance of the pipe in the soil. And that's what the box is. And you can see the size of the box because you may see a person next to it. So it's much higher than this person on this particular, you can see from the photo. And then what you see on the other photos, and then the picture on the video that on the left is really how we test the pipeline, like a plastic pipeline that you see on your neighbor, what's being installed in your neighborhood. And you can see how pipe can bend without leaking. And then you see on the left, we do a variety of testing of pipelines like bending, putting in tension, compression, combination of these forces to understand how these pipeline, including the joints and the other facilities like valves and etc., will perform. If we go to the next slide, I think you may see one of the tests that we did. This is a test on what we call is a ductile island pipe with a special feature at the joint that it can rotate as much as possible without leakage and to cope with the earthquake fault ground movements. So what we're doing is that we're bending a little bit, and then you pulling a pipe to see when does it sort of break. As we pull, you start to see no leakage up to this point. And then what you see is that at some point, it starts to leak a little bit. And then we start to understand what is the actual performance of these pipes. At the same time, we do a lot of engineering analysis of these pipes. So if you go to the next slide, these are called finite element analysis, where we look at the details of the joints together with the manufacturer US pipe here together, try to see you bend it, and then you start to pull it, and you see the details of the failure mechanism, so we can improve the joint behavior. Now, maybe we can go back a little bit, one slide, if it's okay, yeah, just to showcase. If you see the pipe, we put a lot of sensors. And one of the things that we do is we put what we call fiber optic sensor. And the lines that you see around is a cable, fiber optic cable that you use for telecommunication. But actually, this fiber optics become what we call temperature, strain, or vibration sensor. We can measure these sort of variables every point along the fiber. And by doing that, we understand the performance of these pipelines better. And that will calibrate our numerical model so that we can look at different geometry, different performance in the numerical simulations. So if we go to slide 9, this is the new technology coming out that I've been working for past 10 years, 20 years or so, but it's really coming to the market where you use a standard optical fiber. It shoots a light from one of the interrogator box that you see in the middle. It shoots a light, but then by looking at a light coming back from every point along the fiber, we can get what is the temperature there, what is the strain there, that is distortion or movement, or what is the vibration, or it can be a microphone to listen to what's happening at that particular location. So we test these systems to get some sort of trying to persuade our colleagues like EBMUD or Clifford, say, wow, this is an interesting technology to use in the laboratory. And the next step is to bring it to the field. So if you go to the next slide, that's what we've been doing. This is a pipeline that is replaced crossing a Hayward fault. You may identify a pool underneath at the bottom of the picture. That is Claremont Hotel. So that is Claremont Avenue. And EBMUD last year replaced the pipeline. At the same time, what we did is that we have put this fiber optic sensor on top of this pipeline to monitor this pipeline against Hayward fault movement. And unfortunately, the text is hiding, but then what we did is that we've been monitoring for some time. And then there's a video showcasing how it's being installed. But the point here is that once we bury a pipeline, we're not going to see it for the next 100 years. So why not bury intelligence during construction for future generations so they can use this data to do a risk assessment of these pipelines if Hayward fault earthquake happens along the Hayward fault. Why do we want to do this? In engineering, if you go to the next slide, we do a lot of design, and sometimes we have to simplify or do some assumption to understand how this pipe and saw behaves, like what you see on the left. These are the engineering analysis. But once you go to the field, often there are some differences from the model. For example, if you open a trench, you may see a pipeline, which is a newly placed pipeline you see in the front. But if you see at the back, you see a little bit of another pipe, which is abandoned pipe. And therefore, we don't know whether the abandoned pipe is going to help this protect the new pipe against default, or it may not be the other, it may be the other way around. So having a sensor in the important location to ensure that our pipeline is behaving correctly as we design is why we want to monitor. Let's go to the next slide. Maybe Clifford, you want to talk about the robotics?
Sure. Yeah. So I think probably one of the most popular staff on the Center for Smart Infrastructure is Spot, the robotic dog. Is from Boston Robotics, and it's really not just for fun. We want to see how we could use robotics to do better types of inspections. And last year we had to inspect a 7,000-foot tunnel that's nearly 100 years old, and we equipped Spot with different types of cameras and sensors to help with that tunnel inspection. And what this does is it really helps us collect more information about the tunnel's condition. Now, the good news is the tunnel, despite it being almost 100 years old, is in great condition. And so as part of the Center for Smart Infrastructure, we want to see what other types of things we can do with robotics and with drones and satellite imagery, and we'll talk about ground penetrating radar in a minute, to really collect more data that we can use and that Kenichi and the university can use to help us do designs that are even better. I don't know if Kenichi, you want to add anything about
No, this is great. Yeah, so we've been doing a lot of one. If you click another next slide, yeah, there you go. You see our colleagues working with the EBMUD colleagues to try this spot in the tunnel.
Yeah, this was a tunnel that goes through the Berkeley Oakland Hills.
Yeah. Next slide, please. So these are video. If you can click the image on the right, you start to see, yeah, there you go. This is what we call ground penetration radar. So it's a bit like an X-ray machine that you carry with your truck, and then you trying to scan the underground to understand where the pipeline is or utility lines are. And often that you can see the actual, you guess from the X-ray image as what we do with a medical sort of a examination. And by doing that, you start to see where the pipelines are. And this helps when you replace the pipeline. Sometimes it's not recorded in the past, and therefore we can see what are the risks while you're excavating and replacing a pipeline. Yeah, so what we're doing right now with this particular technology is really trying to see what's the value. How can we increase the process of construction? What is, if we use this technology, what is the, can we avoid some of the difficulties, but at the same time, what are the savings that we can make while replacing pipelines?
Yeah, I was just going to add, Kenichi, I mean, like we're all used to seeing, all the infrastructure above, the roads, the buildings, the bridges. I mean, these are the things that we can see. What we don't see is what's underground. And, I talked about the 1.2 million miles of water pipe. But if you look at the sewer pipe, the natural gas, the telecom, the electric, in the United States, there's 20 million miles of underground utilities. And when you do work in the streets and when you design things, if you had more accurate information about what's underground, you can do better designs, you can construct faster, and you can also make sure that your construction is safer. So, this is really, great technology that we're seeing how we can use to do our work better.
Yeah. Next slide. So now we've been talking about, up to now, we're talking about how pipeline behaves, how the asset behaves. As an engineer like me wants to know exactly how they behave so we can predict the future performance of these pipelines. But like Clifford, who's the general manager of EBMUD, is really his interest is to make sure that you get your water as in your every houses that he looks after. So that is a service performance. So how do we link those together is where we do a lot of simulation from the pipeline level to the entire EBMUD network, for example. So you see on the right is the water network of the EBMUD, and we can simulate the water supplies at every pipe from the pipeline level to the entire EBMUD network. What you see on the left is that every road has pipeline. So we can do is that we also simulate traffic on top of the pipeline. And we have about 7 million people in the Bay Area. Every day, there's about 15 million trips. So we can model every 15 million trips and cars moving around in the simulation. And for example, if the Bay Bridge it has a problem, what's going to happen to the traffic and that kind of thing. So we can do that kind of simulation using what we call high performance computing. If you go to the next slide. So for example, you may have a Hayward Fault earthquake. So like step one, you have an earthquake scenario. Every location of the epicenter will shake the ground in a different way. So we simulate different scenarios of earthquake. Every location will have a different ground shaking. That will tell us what are the potential pipeline damage it has for a given earthquake. And then we do a water network simulation of which customers may not get water with these pipeline breaks. Obviously, we don't know exactly where the earthquake is going to happen. It may happen along the Hayward Fault, but we don't know. So we do a lot of simulations to get what are the average water shortage, but what are the variation that it may happen. So that helps us to understand what are the magnitude of the damage that EBMUD pipeline may have if a big earthquake happens. At the same time, we do simulate of potential red tag buildings and also traffic disruption. So we look at interdependency of these things. And then the idea is that now you have certain number of breaks for EBMUD. How do you bring it back to the normal service? And that's something that we're working together with Clifford's team to see what can we prepare now so that if the big earthquake happens, how do we bring it back in a most cost-effective but time-effective way? So it's really about developing strategy, response, and recovery plan. And that deals with supply chain. The other things that we've been working in is wildfire. So you may remember the Camp Fire in 2018 in Paradise, and you may remember the devastation that we had on that particular fire. What happened was that particular day, fire happened around 6 o'clock in the morning. By 7 o'clock, 8 o'clock, it started to move to Paradise. And then it consumed Paradise within about 1 hour or so. Paradise, city of Paradise, town of Paradise had a award-winning evacuation plan. But the assumption behind was that the fire will come slowly and there's a time for people to evacuate in a what we call staged evacuation manner. However, the colleagues, law enforcement officer and the fire chief in Paradise had to call for immediate evacuation because fire was coming so quickly. And now you see a fire creating a fast evacuation and then creating a traffic jam that you see on the right. So if you go to the next slide, we do simulation of the wildfire. At the same time, we do traffic simulation. So what we see in the on the right figure is to simulate that particular day from people from the Paradise evacuating either to Chico and Orville, but many people go to Chico because the fire was coming from the sort of south, east side. But what happened is that the communication between the Paradise and Chico in terms of traffic lights was not very effective. And therefore, there were 3 traffic lights coming into Chico from Paradise was not effective. And that created a long queue, a long line for the traffic to evacuate. So by doing that, we can start to simulate and understand what happened that day, but also we can start to do simulation. If you have less vehicle for using evacuation, many people want to use many cars when they evacuate to bring all the things, but in certain scenarios, You want to have less cars to make effective evacuation. Sometimes in this particular case, cell tower went down during the evacuation. So what is the effect of that in terms of less communication during evacuation? So we do wildfire evacuation in terms of wildfire simulation that you see on the left top. We do traffic simulations, but also more importantly, we work together with social scientists to develop a communication model. And these are called what we call digital twin models, trying to create a virtual model of what we can see. And then, but then we're bringing social scientists to understand how it behaves. And that is where the communication model comes in. And we call it socio-technical digital twin, which is a new it's an area of research for us. Once we have the results, what we want to do is to communicate that results to public as well as the people working on wildfire. So there's we have a project funded by the National Science Foundation where we work together with a team of colleagues at UC Santa Cruz who develops what we call serious games. So it's really about creating a game coming out from these scenarios of the simulations and trying to see how can that particular issues can be communicated to the public and also people in danger. Everybody has a different way of understanding the risk, but then by doing these games, hopefully the community will understand the risk collectively together. And sometimes when you make a quick decision, it's not that you have to wait for the law office so the government to say something. It's really the community coming together to make the right decision by doing these games. And that's what we're hoping to happen through the working with the community to appreciate the risk, and therefore they make a right collective decision during evacuation.
Yeah,
Next
I think,
slide, please.
yeah,
Oh, sorry,
I was
Clifford.
just going to say, one of the good things about this one is, I mean, this is for wildfire, but you could also do it for water utilities and how well people are prepared at home and have enough water supply, because, you know, if the community is better prepared, it makes our response faster. And so this is really a tool to educate the community, and we could also use it for our employees as well. If you go next slide, you know. So, I mean, there's a lot of stuff that we're doing, and you heard a lot of that from Kenichi, but we have been focusing a lot on pipelines, and there's a good reason for this. And so what you see here, we looked at the capital budgets of the 11 largest public water agencies in California. And those agencies represent or provide water service to about 2/3 of California. The majority of the projects is what we call the linear infrastructure or the pipe. So in the next 10 years, you know, those agencies, including EBMUD, is going to invest over $5 billion in pipelines. So this really presents a great opportunity to work between the agencies and the CSI to see how we can do this better, because there's so much money going into the pipeline. Next slide. You know, the other benefit of all those investments that we make is it really supports lots of local jobs and businesses. And, you know, this data is for EBMUD alone, but in the last couple of decades, you know, all that investment of our infrastructure led to $350 million to local businesses, $94 million to small businesses, $36 million to ethnic, minority, and women-owned businesses. And you can also look at the local and minority hire. So, you know, these types of investments not only are good to build a resilient water system, but it's also good to help the local economies as well. Go next slide. So this is the other really fun part about the CSI. So not only are we trying to solve the problems with our infrastructure, but we're also looking, how can we create a pipeline for that future workforce, for our future leaders? And so as part of the Center for Smart Infrastructure, we sponsored a class on water and wastewater operations and design. And you can see what we're teaching. We teach about our water supply. We talk about water system design, infrastructure maintenance, sustainability and resilience, emergency preparedness, water policy, judgment and decision-making, you know, all things that are really important for engineers. And what we found, we've taught this for 2 semesters now, and what we found is, you know, many of those students going into the class really didn't think about a career in the water industry. And it really opened up their eyes to the work that we do and how exciting and challenging, of a field that we have. We also found that the students today, and I don't know if this is generational, Kenichi, you would know this better because you've seen generations and generations of employees or students, but this generation really cares about the environment and they really care about the community. And I was at a career fair at Berkeley, and this was East Bay MUD was the only public utility at that career fair, and there were other high-tech industries there as well. And there are electrical engineers and mechanical engineers and some civil engineers in the room. And I remember a person came up to me, and the first thing they asked me, they didn't ask me about what does the job pay or what would I do. The first thing they asked is, what's East Bay MUD doing about sustainability? And that's what they care about. And if you get into the water and wastewater industry, that's what we are all about. We are all about protecting the environment. We are all about protecting public health. And so when you have students that want a purpose, there is a really great purpose to the work that we do here at East Bay MUD. You go next slide. Yeah, so these are two students, I think, is Ivan and Christina, and they work with East Bay MUD to present at a Berkeley data science exposition. And these students didn't realize how much we use data and use data science to solve and try to address our problems. So they worked on a pipeline project of ours. You go next slide. And Kenichi, you could probably talk more about this, but it's not just the students at Berkeley, but we want to reach to the high school students. So you want to talk about what you did here?
Yeah, so these are the high school students who 4 of them spent last summer working together. We were trying to understand how we can use ChatGPT to collectively put the information together on the water information about water, and the students learn about how to use ChatGPT or how to do language learning, create a language model for that. And then the students worked in the lab to do some testing together. And so you can see, we hope these students, and actually one of the students now is a UC Berkeley civil engineering student.
There's a lot of other research that we're interested in working with Berkeley. I'll just touch on a few of them. There's more dam research that we want to do to understand how dams perform and how spillways, the components of the dams perform. And a lot of these sensors and modeling will help us out. We have, like all utilities, we have large transmission pipelines, 120 inches in diameter, that are particularly challenging to monitor. And we want to use a lot of these sensors and the fiber optics to monitor that. And these pipelines cross different types of hazards like landslides. And we want to understand how these landslides over time affect our infrastructure. You heard Kenichi talk about some of the wildfire monitoring, but we can also use that modeling to help inform how we can better manage the vegetation in the watersheds that we manage. There's more climate and water supply modeling that we're interested in doing, monitoring the watersheds to see, you have all the snow in the mountain. Well, how does that snow translate into runoff into the rivers? Can we get more precise and accurate estimates on what that runoff will be? And then we also want to look at advanced metering infrastructure. These are kind of those smart meters that you might put on the water meters. And this type of project for East Bay MUD, for example, it's very expensive. It costs $200 million to install smart meters for all of our customers. That's a lot of money to spend. And so we want to work with Berkeley to see, can we get most of the benefits of advanced metering infrastructure, but installing fewer of these devices. So to really be more cost effective about how we do this, but use the data that we collect to inform better decision making. You go next slide. So when the CSI started, we didn't really know what we were going to get into. And we had a few partners at the time, Los Angeles Department of Water and Power, San Francisco Public Utilities Commission, and the Metropolitan Water District of Southern California. And so we started with 4 workshops. The first workshop was for the academics to hear what are the challenges that utilities, the infrastructure owners, are facing. The second workshop was for the infrastructure owners, the utilities, to hear what are the academics interested in researching. The third workshop was to try to marry the two, find where there is common interest. The fourth workshop was on community preparedness. We've actually had a 5th workshop since to see how consultants can help us out Since then, we've added a few other utilities are interested, like the Contra Costa Water District and the Alameda County Water District. And these workshops have been very beneficial in kind of developing the business plan for the CSI. I don't know if you want to add anything else, Kenichi?
Oh, this has been a great one to really understand the sort of issues that our infrastructure colleagues, infrastructure owners have, but then trying to link with our researcher academic interest to make sure, and then more importantly, our researcher and the students really get excited that they're really working on some problems that our infrastructure owners are facing. So it's been a great workshop.
Go next slide. And so like we've been saying throughout this presentation, we have to collaborate to solve these problems, and that's the collaboration between infrastructure owners, academia, consultants, industry, and the regulators. And it's really about finding innovations. And if you look at that kind of that flow chart, at the end of the day, what we're interested in is creating a market, creating services or products that can help us solve the problem. And Kenichi and his colleagues, they want to do research that solves the problems. They don't want to do what they've called, they don't want to do lost in space research. They don't want to do research that just sits on the shelf. They want to find solutions that solves our problems. And that's really exactly what we're looking for.
And importantly as well is that we are in the sort of Bay Area. We talk about Silicon Valley. We talk about entrepreneurship. The university talk about that a lot. But it's not really just making money. It's really about at the end, and what we want to really focus on is really saving for infrastructure owners. If we can introduce this technology, how can we make sure that we can make savings so that the water rate, paying your water doesn't have to go up. So that is what we're trying to do. Be more proactive by having sensors and data, more proactive actions rather than reactive actions. And then having our energy and water affordable, keep affordable. And that's what we want to focus and show the value of these technology to make this happen. And that's what the main purpose of the center. If you go to the next slide, this is a little bit what we do. You can show that we have a big laboratory at Richmond Field Station, which is in the city of Richmond. It's part of the UC Berkeley sort of a laboratory testing facilities. This is one of the pipeline. It is designed to withstand large deflection by the ground movements. You can see our students attaching, we call fiber optic sensors, trying to get a lot of data from one test. The pipe is pressurized, and therefore you have a water inside so that we can mimic the actual condition. And then you see a joint in the middle where it's going to bend. And this is called 4-point bending test, where you see a pipe being bent. So you see a two loading system pushing down to create what we call a moment, to create a bending. And you see a lot of cable that is measuring strain or movement at every point along the fiber. And this is where the pipeline is moving. It's going up to 22 degrees. And as you see, more and more bending, it's happening. And you can see it's still not leaking, even with that particular angle. Oh, and then finally it breaks, and then the water comes out. And so we understand how these joints move. So how can we better design the joints, but how we can monitor these pipeline systems so the sensor can be deployed in the field, and therefore what we measure here can be checked in the field and to make a right decision, because actually pipe is buried in the ground, so you're never going to see what's going on. So this is our final slide. If we go to the next slide, I just want to finish off from my point off is that Lord Kelvin in 1883 said that if you cannot measure it, you can't improve it. So what we're focusing in the Center of Smart Infrastructure is to use a state-of-the-art sensing technology, data analytic tool to make sure that we measure it so we can improve how we use our infrastructure. So CSI is not only a think tank, but it's more importantly, it is a do tank. We just want to make it happen. Clifford?
Yeah, I'll just kind of add, I mean, the idea for me behind the CSI is really to solve, and I've shared this with Kenichi and all his colleagues, but it's really to solve, what I would call those crazy big problems or the crazy big ideas. And so you might ask, like, what does that crazy big, problem mean? And what's that definition? I heard this before. I really love the definition. And to me, what that crazy big problem is there's really four things. If it doesn't move you, if it doesn't scare you, if it doesn't excite you, then it's not big enough. If you could solve it on your own, it's not big enough. If you could solve it in a year, it's not big enough. And if there's a clear path to the end, it's not big enough. And so we're really trying to solve the biggest problems that our industry is facing. And we're really happy to have this partnership, not just with UC Berkeley, but with all the other partners, because we're in it together. And we know that we have to work together to solve these problems, these crazy big problems. And we are really excited that Berkeley is so invested in the Center for Smart Infrastructure, because I think it's going to do a lot for our industry.
Thank you. Thank you so much, Clifford, and thank you, Kenichi, for an amazing presentation. And thank you, everyone, for being patient as we were working through some of our slides. I am now going to turn it over to my colleague, Catherine Horn, who will begin the Q&A, and I will work on that last slide as you start, Catherine.
Okay, that sounds great, Anna. Thank you so much. And thank you so much, Kenichi and Clifford. I would love to have Spot as my dog. He seems very, very helpful, to say the least. So we have some really great questions in the queue. And again, if I can't get to all of your questions tonight, you can always email us at waterwednesday@ebmud.com if you think of something later on. We're going to try to answer as many as we can, but we will end right at 7. And then Ian, I just pulled up just a reminder that for our next Water Wednesday, we will be holding it on April 24th, Wednesday, April 24th at 6 p.m. It's going to be an annual water supply update with Dave Briggs, who is our Director of Operations and Maintenance, and Mike Tognolini, who is our Director of Water and Natural Resources. So hopefully you can join us then. So with that, I'm going to pull some of the questions that I've flagged. So what is the most promising material you are testing and finding that would last a long time, like 100 years or more, and not degrade, compromising water quality?
Clifford, do you want to start that?
Yeah, I mean, there's different pipe materials that we've tested. We've tested plastic pipe, we've tested ductile iron pipe, and there's steel pipe. There's different types of materials. I think for East Bay Mud, our standard material going forward is going to be ductile iron. We've historically had cast iron pipe, which is similar to ductile iron, not entirely. But ductile iron, I mean, there's earthquake resistant ductile iron pipe that's very earthquake resilient. There's one type that's used in Japan. I think it made it through some of the largest earthquakes in Japan without a single leak. So we're very pleased with this. But I will say, like, while we've standardized on ductile iron pipe, there are times where we want to use different types of pipe materials, depending on the conditions. But for the most part, I think the most promising material for us that we think meets, checks all the boxes. And when you think about the boxes that we're trying to check, there's really 3 things we want to make sure. The first thing is, does it have the right engineering characteristics? The second thing is it easy to install? And then the third thing, which is the long term, is it easy to maintain? I mean, there are pipes out there that have really great engineering characteristics, maybe a little more challenging to install, but next to impossible to repair. And so while it may be great from an engineering standpoint, and while it may be great to install, long term, when you have to maintain it, it'll be very, very difficult. And so we care about all 3 aspects when we're looking at the pipe material. So, but for East Bay Mud, we really landed on ductile iron.
So another question, just to piggyback off of that, they were asking specifically about ductile iron, and if it is properly managed and maintained with cathodic protection, can it last longer than 100 years? And why not be more ambitious when we talk about the life expectancy of a pipe?
Yeah, I mean, that's why we do the testing. I mean, we 100 years to me should be the minimum. I mean, I like to see 150, 200 years out of these pipes. If it has the right protection, and we've tested different types of materials, if it's bonded properly, if it has, the right corrosion protection, conceivably, it could last a very, very long time. I mean, we have cast iron pipe that we you have taken out of the ground that's 150 years old and it looks brand new. And that's great. So I think we can expect the same thing with ductile iron pipe as well. You know, and plastic pipe, again, we have plastic pipe in the system as well. That track record doesn't have as long of a track record. But I think the engineering characteristics that it probably could last as long as well. I don't know, Kenichi, do you have any thoughts on this?
No, what I want to say is that that's part of the reason we want to put fiber optic sensor. Fiber optic sensor will last for many, many years, more than pipeline perhaps, because it's made of silica. The point here is that if you can attach that sensor and then give it to the next generation, what you do not want is that you open up and find out your cast iron of your pipe is very, very nice, although you thought it's going to be aged and you have to replace it. So that is a waste of money, so that because you can use it for another 50 years. So if we can attach these sensors and then give that information to the next generation, they can use it to say, okay, when should we replace the pipeline? Because the soil condition may be different. You may have a climate change issues. You may have a change in usage because you may be changing the pressure or the way you use it. Every pipe will have a different characteristics because of the environment they're in. So if we can put sensors right now, perhaps that will help the next generations.
So I actually had a question based on that. So you showed the pipe being installed over by the Claremont Hotel. Do we have plans for future pipe installation to include the fiber optic sensors, and how many feet, and what's the plan for that?
Yeah, well, I mean, I'll start first. I mean, the answer is yes, but I think the other part too is, if this works well, I mean, it would be, and this is why we want to work with industry. It would be nice if we could buy the pipe with the fiber optics installed on it, and then we don't have to install it afterwards. And so if we can prove this technology, this could be part of the product. Kenichi?
No, that's absolutely right. It's really we're trying to see the value of this sensor. Of course, you have to invest a little bit, but then if we can show the value. So we've been monitoring to see, wow, this particular sensor can give this information. Then what is the value? If we have this, do we want to do it at certain locations, or are going to do every location? And then there's a question about leakage. This fiber optics can become a microphone at every point. So it can start to listen to leakage if there is creating some acoustic noise. And we do see some companies that EBMUD, and we work together. It's one of the worker is my former PhD student, and they're using a fiber optics already installed in the street for telecommunication purpose, but you can use that fiber to listen to what's going on around that particular fiber, like what's going on the street, or is it leaking happening or not. So EBMUD is prototyping, trying that as a trial, which is happening right now.
Yeah, and that student was the one that helped you with the Claremont
That's right. That's
pipeline.
right.
But what's really exciting about that is we're using somebody else's infrastructure, the telecom industry, and using what they've already put in the ground to help us for leak detection. And so we're leveraging each other's technologies to benefit each other.
Mm.
So just one little brief mention that someone had mentioned that so technologies change so rapidly that sensors may become obsolete faster than 100 years from now. Is that something that you guys are considering?
Yeah, so absolutely right. And then certain sensors is mechanical sensor, so a sensor does degrade. But this fiber optics for me is a really unique technology because the fiber is the sensor. It's made of silica, and in terms of material, it won't degrade. But then the box that you saw, which is attached to the fiber, you can change it as the technology improves, in a sense that potentially the data becomes better and better with time, because the box changes, the technology changes, box become cheaper, so it becomes more easy to use. So for me, it's a interesting technology, but then that's exactly what we want to do, is to understand the sensor, how the sensor degrades, because the sensor degrades faster than the pipe, it's not useful. So that is a very important aspects of these infrastructure sensing that many of our colleagues in electrical engineering don't understand, because they look at these products to be very short-term products, cycle products.
Yeah,
Very good
I
question.
think what's really exciting for me about the fiber optics is exactly what Kenichi's talking about. We've worked with companies that want to attach these devices to the pipe. It's very expensive to dig a hole, attach something to pipe that will only last 5 to 10 years as a sensor. But the sensor itself is a fiber optic, and the part that we can easily replace is above ground, then we don't have to worry about digging up the pipe, because the sensor is will last as long, or as Kenichi said, maybe even longer than our pipeline. And that's really exciting for us.
You. So we had a question that says, can you simulate how the water infrastructure would withstand an earthquake at various magnitudes given the current materials?
Yes, so our simulation looks at what are the current materials. So EBMUD provides which location has what kind of pipe, what is the diameter, and that sort of thing. And we have a model, what we call it fragility curve, is that if you have this ground shaking or ground movement, this is the probability of failure. So every pipe, we know how model-wise it does. And then we do a simulation of an earthquake of different magnitude. And then for if you have a Hayward fault epicenter somewhere in the Hayward, you have a one shaking and then see how pipeline may break. And then if the epicenter becomes in Berkeley, it will have a different shaking, and then it will give a different performance of the pipelines. But we never know which one is going to be real, because these are simulations. So simulations allow to understand what are the possibilities, what are the uncertainty, what are the risk, what are the things that we should prepare. So wildfire is the same thing. There's no optimum solution to these problems, but it's really for us to understand what may happen, what can happen, so that once something happens, we are prepared collectively with our knowledge to work together in the right way, so we can make our pipeline functional as fast as possible. So it's a great question, and we can do it, but then the motivation is not optimization. It's really trying to showcase how we can increase our knowledge.
So this one is kind of a pretty broad question, but Clifford, I'm going to give it to you. And I think maybe this question came in as we were talking specifically about earthquakes, but how can we as customers be prepared?
Yeah, I mean, I think the first thing is make sure you have enough water at home. Because, I mean, the reality is, after the earthquake, there's going to be a lot of main breaks, and it's going to take time for the water to be restored. And, we're working with the various counties and cities to look at how that water can be distributed to the customers after their supply at home exhausts. So, excuse me, that 7 or 14 days of supply that you might have at home, that's really just enough water to get you through to find more water afterwards. And so if people are better prepared at home, it's going to make our response better. I think other things that you really should do, you should talk to your family. What are your plans after the earthquake? Whether it's a fire or an earthquake or anything, you need to be prepared of like what are you going to do? What if you can't live in your house anymore? Where are you going to go? What are your backup plans? The better prepared our customers are, the faster we can respond to emergencies.
So I think we have time for just one more question. The question was about using plastic pipes. Are we concerned at all that plastic is going to degrade, flake off? And if so, how can that be detected or removed before it enters a person's home?
Yeah, so plastic pipe, I mean, everything that we put in the ground are, what we call NSF certified, so National Sanitation Foundation, not the National Science Foundation that you work with, Kenichi. Everything is tested and certified to be safe for potable use. There have been certain circumstances where plastic pipe, you might have heard in Santa Rosa during wildfires, that certain chemicals have leached out. We're actually part of a research project to understand that better. But I think that understanding will help lead to better designs. But everything that's used, whether it's plastic pipe, steel pipe, ductile iron pipe, everything that we use has been certified to be safe for potable use.
Well, thank you so much. So I think that kind of ends the questions that we've had come in. And I just want to remind everybody that if you do have additional questions that you think of later, please feel free to email waterwednesday@ebmud.com. With that, I think we can end with 1 minute extra. So Thank you so much, Kenichi and Clifford and
Thank
EBMUD for facilitating tonight, and everybody for joining.
Thank you.
All
Thank
right,
you very
have a good night.
much. Yeah,
Okay, thank you so
thanks.
much. All right, bye.